Yeah, very good afternoon all. Today we are going to discuss about the relations, which is a topic in the discrete mathematics and logic for the second BTech AIML of third semester students. Okay, we will see from the basic definitions. I will let you know what is a relation and what are the types of relation we are having. So let A and B be the two sets. So for example, consider two sets. Then a relation R from set A to set B is a subset of A cross B. Okay. Thus, R is a relation from A to B. So and so R is subset or equal to A cross B. Okay. If A comma B belongs to R, that is, we write A related to B. Okay. We write it as A or B means A is related to B by relation R. So if A comma B not belongs to R, then we can write A is not related to B, okay, by the relation capital R. So relation is nothing but some correspondence, some correspondent. For example, if I am teaching one student, for me he or she is a student. That is a relation between. Okay, so I am related to that student as a teacher. So similarly, in the binary relations also, if element A belongs to one set and B is belongs to another set, then A comma B is nothing but forming a one relation that the such that A is related to B by means of some particular property or relation. So if the number of elements in A is equal to M and number of elements in B is equal to N, then A cross B has M n ordered pairs. Therefore, total number of relations from A to B is 2 power Mn. So next thing is, what are the types of relations? We are having majorly three types of relations: reflexive relation, symmetric relation, and transitive relation. Okay, so in today's presentation, we will see these three. So a relation RE on a set A is said to be reflexive if every element of A is related to itself. That's R is reflexive such that A comma A belongs to R for all A belongs to capital A, that is set, all the elements of a set. A relation R is not reflexive if there exists an element A belongs to A such that A comma A not belongs to R. So for example, consider the set A is equal to 1, 2, 3. Then the relation, if we consider one relation, R is equal to 1, 1, 2, 2, 3, 3, 1, 3, 2, 1, which is a reflexive relation on A. Why? Because is in A three elements are there, 1, 2, 3. So 1, 1 is a 1, 1 is a one of the element in relation. 2, 2 is one of the element. 3, 3 is another element. So it is reflexive. We are not bothering about any other elements of the relation while considering a reflexive nature. So if the whatever the elements are present in the original set, if those elements are satisfying the property of A comma A belongs to R, then that will be the relation is said to be reflexive relation. But consider R1. R1 is given by 1 1 3 3 2 1 3 2. So it is not reflexive. Why it is not reflexive? We are having the original set 1 2 3. In that one, 1 is satisfying reflexivity, 3 is satisfying reflexivity, but 2 is not satisfying because 2 comma 2, that element is not there in this R1. So that's why it is not reflexive. Next, symmetric. A relation R on a set A is said to be symmetric if A comma B belongs to R, then B comma A must also be belongs to R for all A comma B belongs to A. So that is A related to B. A is related to B by means of a symmetric relation. Then B should be related to A for all A comma B belongs to A. So let A is equal to 1, 2, 3, 4 and R1, R2 be relations on A given by R1 is 1, 3, 1, 4, 3, 1, 2, 2, 4, 1 and R2 is 1, 1, 2, 2, 3, 3, 1, 3. Here if you consider this one, the relation R1 is symmetric. Why? Because is 1, 3 is there, 3, 1 is there, 1, 4 is there, 4, 1 is there, 2, 2 and 2, 2. So R1 is symmetric. But R2 is 1, 1, 2, 2, 3, 3, 1, 3. Here 1, 3 is present, but 3, 1 is not present. That's why R2 is not symmetric, R1 is symmetric. A reflexive relation on set A is not necessarily be symmetric. For example, the relation R is equal to 1, 1, 2, 2, 3, 3, 1, 3 is a reflexive relation on set A 1, 2, 3, but it is not symmetric. Next, transitive relation. Let A be any set. A relation R on A is said to be transitive if A comma B belongs to R and B comma C belongs to R. Then if A is A comma C also belongs to R. This is the transitive relation. So A related to B by means of some relation, B is related to C by the same relation, then A is related to B, C by the relation. That is the transitiveness. For example, on set of n natural numbers, the relation R is defined by X is related to R, X is related to Y by relation R, X is less than Y is transitive because for any xyz, if x is less than y is less than z, then x is less than z. Okay. Next, take another example. Let A and B the set of all straight lines in a plane. Then relation is parallel to on A is transitive relation. Okay. Because for any line 1, line 2, line 3 belongs to A. Because L1 is parallel to L2 and L2 is parallel to L3, then L1 will be parallel to L3. Okay. Similarly, there is some example. Check the relation R for reflexivity, symmetry and transitivity, where R is defined as L1 is perpendicular to L2 if and only if L1 is perpendicular L1 related to L2 if and only if L1 is perpendicular to L2 for all L1 L2 belongs to A. So let A be the number set of all lines in a plane given that L1 is related to L2 such that L1 is perpendicular to L2 for all L1 L2 belongs to A. So reflexivity. R is not reflexive because a line cannot be perpendicular to itself. Okay, or this relation, perpendicular relation is not reflexive because a line cannot be perpendicular to itself. So reflexivity is not correct. If the property is not following reflexivity. Symmetry. If L1 is perpendicular to L2, then L2 is perpendicular to L1. So the relation is symmetric on A. Transitive. We'll consider the three lines which are L1 perpendicular to L2, L2 perpendicular to L3, then L1 need not be perpendicular to L3 because if you consider the geometry, linear geometry, L1 is horizontal, L2 is vertical upwards, L3 might be vertical horizontal leftwards. So that's why L1 will not be perpendicular to L3. You can check by drawing some small diagrams. Next, equivalence relation. A relation or on a set A is said to be equivalence if and only if it is reflexive, it is symmetric, it is transitive. That is, when the relation is satisfying these three properties, it is said to be equivalence relation. So, for example, uh, The equivalence is represented by this congruent 2. Okay, and the it is represented by three, the symbol like this, two horizontal lines equal to over that similarity. So it is consider a relation is congruent to. Okay, it is reflexive because a triangular, two triangulars, let us assume that the triangular, if two triangulars are similar or is congruent, then that will be reflexive, because if one triangle is congruent to another triangle, then second triangle is also congruent to first triangle. Next, symmetric, because if triangle 1 is similar to triangle 1 is related to triangle 2, then triangle 2 is also related to triangle 1. Okay, so it is symmetric. Transitive, because if triangle 1 is congruent to triangle 2 and triangle 2 is congruent to triangle 3, then triangle 1 is congruent to triangle 3. So that means it is equivalence. Is congruent to is a relation that will satisfy the equivalence property. So this is one more example. We have to show that relation R defined on set A of all triangles in a plane as R is equal to T1 comma T2. T1 is similar to T2, is an equivalence relation. Let us consider one triangle. If you consider one triangle, that triangle is always similar to itself. So that's why this particular R property is satisfying the reflexivity. Second one, let triangle 1 is triangle similar to triangle 2. Okay, triangle 2 is similar to triangle 1. Then triangle 2 comma triangle 1 is also similar to, uh, that is, if T1 is similar to T2, T2 is similar to T1. So that's why R is symmetric also, transitivity. If we consider the three triangles, if triangle 1 is similar to triangle T2, so triangle T2 is similar to triangle T3, then triangle T1 is similar to T3. So it is satisfying the transitivity. Since it is satisfying the three properties, R is an equivalence relation. This R relation defined here is an equivalence relation. Okay, so thank you.